Yeah, our next speaker is Zac McEachran from Soil, Water, and Climate Department. And I'll ask Shankong Mu to prepare for the next.
Yeah, thank you. I appreciate it. So I'll start off by getting everyone up to speed on catchment science. So I'm going to say that stream flow is the vital sign of a catchment, which is an area unit of land where if you drop a water on it, it's going to flow through that point in the stream, right? So you stand in the stream and you look uphill and everything is the catchment, right? So I'm a catchment scientist. So it's like when I go to the doctor, I get my blood pressure and heart rate taken, but I wouldn't say that's the same as my health, right? It's sort of an indicator of what's going on in my body as a whole. Similarly, I put my stethoscope up to that red dot at the outlet of the catchment and try to figure out what's going on all throughout that watershed. Now, as a catchment modeler, you maybe do something like there on the right, where you say, well, there is something with soil moisture, runoff, groundwater, et cetera. I have my inputs, precipitation, and I want to try to forecast my stream flow outputs. I develop out my process-based model. I use my weather forecasts. I first estimate those catchment physical states based on the physical laws, and then I develop my stream flow forecast. When you're forecasting, though, in particular, you want to be able to alter those states as you go, right? Because maybe you get additional information as the time series marches on. Oh, my representation of soil moisture was too dry because now the flood is outperforming what I'm forecasting to start, right? So at the U.S. National Weather Service, for example, a human forecaster will go in and manually alter the states to make the sort of best guess forecast that's out there. So how is this done in the machine learning world right now? You typically see some kind of an autoregressive LSTM that is able to, every time step, look at the most recent observed stream flow and then develop your forecast. In that way, the model is somewhat responsive to the observations as they come in. But you can see that that is still mostly an approach that is going to be at a particular gauge. And you can see all of that context that goes into the gauge. I've made a cross section there out of those big cubes. And you can see that it's not only heterogeneous as far as like the process, but also just the context, right? Like each one of those individual cells is not going to be the same as the ones around it because of that context. So colleagues and I have developed a encoder decoder based LSTM based, we call it the factorized hierarchical neural network, or FHNN. It's shown really great scale at the basin level because it takes most recent observations through the inverse model and develops out where we've explicitly told it to develop a representation of slow moving states. That'd be something like maybe snowpack that varies over in Minnesota about half the year, right? To medium, like a water table, to fast, like soil moisture that fills up during the course of a single storm, and all of a sudden you're producing flood-inducing runoff. You can see on the graph, on the y-axis, the error, the x-axis lead time. You can see the NWS human forecaster actually has the lowest error of all three methods still. Yay, humans, right? But our FHNN method towards in that very short lead time eventually eclipses it in the kind of middle lead times. So promising method and a little more interpretable, hopefully. Thank you.